Welcome to the Explainer. I am so incredibly excited to walk you through today's topic. We're going to be looking at the invisible scaffolding that actually powers the digital world, how we organize data for maximum speed and scale. If you've ever wondered how tech giants process petabytes of information without skipping a beat, or, on the flip side, why a poorly designed system might suddenly just crash and serve up stale, inaccurate data when it's under pressure, well, it all comes down to architecture. Specifically, we are going to master data normalization, joins, and the highly specialized schemas designed exclusively for heavy-duty analytics. Let's just dive right into the core problem we're trying to solve here.
So, imagine you're a senior business analyst at a massive international supermarket chain. You're tasked with answering a critical, yet seemingly simple question. Which brand of baby food is most often purchased together with brand X diapers? Now, to get that answer, you aren't just looking up a single receipt. No, you have to scan over an unimaginably huge number of transaction records. You've got to group those records by store region, filter them by specific time windows, and calculate complex aggregate statistics just to find those correlations. But here's the catastrophic catch. How do massive analytical queries process millions of rows without bringing the live operational systems, like literally the cash registers at the front of the store, to an absolute grinding halt? A query this heavy consumes immense compute and memory. And if it locks up the database tables to do its math, well, your customers can't check out.
Solving this huge bottleneck really starts with understanding how we store the data in the very first place. And that brings us to our fundamental core concept, normalization. Normalization is the rigorous practice of structuring data to minimize redundancy. In a highly normalized database, you keep a single, pristine copy of each record, and you use unique IDs, specifically known as foreign keys, to link data together across different tables. Think of it kind of like a meticulous single-copy filing cabinet. If an employee's job title changes or a supplier updates their corporate address, you update that information in exactly one place. The value here is absolutely tremendous for maintaining strict data integrity. By storing data exactly once, you completely eliminate update anomalies. You never have to worry about one part of your system thinking a user lives in New York while another part thinks they live in London.
But, data architecture is entirely about give and take. On one side of the coin, we have normalization. Because there's only one authoritative copy of the data, it's incredibly fast and safe to write to. However, it's inherently slower to read, because the database engine has to actively piece all that fragmented information together from multiple tables just to construct a single human-readable view. Now, on the exact opposite side, we have denormalization. This is basically the equivalent of printing out precompiled, fully comprehensive summary dashboards for instant reading. It's drastically faster to read because all the pieces are already connected and sitting together in a single row. The penalty, though? That comes during the write process. Denormalization suffers from write amplification. If a user updates their display name, the system might have to manually hunt down and update 1,000 denormalized timeline entries just to keep everything consistent. That's computationally expensive and, frankly, risky.
This fundamental trade-off perfectly mirrors how organizations actually utilize databases out in the real world. Let's compare the two primary workloads. First, we have OLTP, or Online Transaction Processing. This is your operational day-to-day workload. These are highly precise point queries fetching individual records by a specific key, representing the latest, real-time state of the data. OLTP systems rely on heavily normalized structures to ensure those fast, reliable writes. Contrast this entirely with OLAP, or Online Analytical Processing. These are the analytical systems built specifically for bulk aggregations over millions or even billions of rows of historical data. Because OLAP requires scanning vast amounts of data sequentially rather than jumping around finding individual records, the highly normalized, fragmented layouts that make OLTP so safe are actually the exact things that make OLAP workloads impossibly slow.
Here's our roadmap for today. First, we'll look at the normalization trade-off. Then, when joins become expensive. Third, schemas designed for analytics. Fourth, fact and dimension tables. Fifth, the Snowflake schema. And finally, embracing model trade-offs.
All right, starting with part 1, the normalization trade-off.
So let's dig a little deeper into this balancing act. We know operational databases lean heavily on normalization for quick, safe updates. But the crucial point is this. When you look at a highly normalized single row of data, retrieving its actual context requires resolving all those foreign keys we talked about. In a relational database, this physical process of looking up and combining information is called a join. You join the user ID to the users table to get their name. You join the region ID to the regions table to get the geographic location.
Under the hood, your database engine is spending precious CPU cycles and memory allocating space to match these IDs together. For a single user profile load, sure, this happens in milliseconds. But as we start asking broader analytical questions, these joins very quickly become the system's biggest bottleneck.
Which brings us to part 2, when joins become expensive.
What actually happens when our queries aren't just looking up one single user, but need to scale up to millions of records? Consider a massive log of user activity events, often called clickstream data, mapping over to a central database of user profiles. If a data scientist wants to know if certain complex multi-step workflows are more popular with enterprise users versus free-tier users, the database can't simply look at the event log. It has to physically map the user IDs from tens of millions of raw event logs to the actual subscription tiers stored in the user database. Performing these joins across enormous datasets is devastatingly heavy. In modern architectures, these datasets are often sharded, meaning the data is physically split across multiple different server nodes. To execute this join, the database has to shuffle massive amounts of data across the network, consuming incredible amounts of RAM and bandwidth. Doing this on your live operational database, it would immediately crash the system. No way around it.
Moving on to part 3, schemas designed for analytics. Because live operational systems simply cannot handle these heavy read queries, modern architectures extract, transform, and load, or ETL, that data out of the operational database and into an entirely separate system called a data warehouse. Inside this warehouse, we completely abandon the strict normalization rules of the operational world. The ultimate solution, and really the most famous analytical layout, is the Star schema. The design is brilliantly intuitive. You have a single, massive table in the center called the fact table, and it connects outward to other descriptive tables like the rays of a star. This schema evolved specifically to optimize bulk reading. By carefully controlling the level of denormalization, the Star schema drastically reduces the number of complex joins required, allowing analysts to slice and dice petabytes of transaction history at lightning speed, all without ever touching the day-to-day operational systems.
Let's break that down in part 4, fact and dimension tables.
Let's walk through how this actually works using our grocery retailer scenario. Right at the center is your fact table. Every single row here is an immutable event that occurred at a particular time, like a single product scanned at a register. It contains raw, unyielding numbers, quantity sold, tax paid, net price. It also contains foreign keys pointing outward. When an analyst runs a query to see if fresh fruit outsells candy on weekends, the query engine doesn't start in the massive fact table. First, it goes to the dimension tables. It filters the product dimension to find the keys for fruit and candy. It filters the date dimension to find the keys for weekends. Then, the engine takes these small, highly optimized lists of keys and passes them to the central fact table, instantly filtering billions of rows down to exactly what is needed before aggregating the total sales. It's like a highly efficient two-step dance.
The real magic of this architecture, though, lies in the rich descriptive context provided by those dimension tables. While the fact table just says ID 5 bought ID 10 on ID 20, the dimension tables answer the who, what, where, when, how, and why. The date dimension encodes deep business logic, like whether a specific Tuesday was a regional public holiday or part of a huge promotional week. And what's truly fascinating here is how dimension tables handle the passage of time, a concept known as slowly changing dimensions. If a retail store expands its square footage in 2023, the store dimension table tracks both the old size and the new size with effective dates. This allows analysts to accurately query 2022 sales data using the 2022 store footprint, maintaining the historical truth of the analytics without corrupting past reports.
Next up, Part 5, the Snowflake Schema. As data warehouses grow, organizations sometimes implement a variation known as the Snowflake Schema. Here, the outer dimension tables are handled a bit differently. Instead of having one incredibly wide, denormalized product table that lists the brand, subcategory, category, and department on every single row, a Snowflake schema normalizes that hierarchy. The product table joins to a subcategory table, which joins to a category table, which joins to a department table. Visually, the schema branches out, looking, you guessed it, like a snowflake. This approach guarantees that complex hierarchical data remains strictly consistent, and it can save a significant amount of storage space. However, analysts often push back against the Snowflake approach. Because it requires multiple hops or joins just to find a product's department, the SQL queries become significantly more complex to write, and the database engine has to work much harder to resolve the reads.
Now, on the exact opposite end of the data modeling spectrum is an approach gaining rapid modern popularity, one big table, or OBT. This strategy aggressively abandons dimension tables entirely. It takes all of that descriptive context, the specific brand names, the holiday flags, the store square footage, and folds it directly into highly denormalized, incredibly wide columns sitting right inside the central fact table. The database essentially pre-computes and bakes in all the joins ahead of time. In the past, this was considered really bad practice due to the immense storage costs of redundant data. But today, storage is cheap, and modern data warehouses use highly compressed columnar storage engines. In a columnar database, scanning a table with 1,000 columns is lightning fast as long as your query only asks for 3 of them. For specific read-heavy workloads where historical data rarely changes, this massive denormalization provides absolutely unparalleled query speed.
Finally, Part 6, Embracing Model Trade-offs. Synthesizing this micro to macro journey of data modeling is essential for any modern technologist. I really want you to anchor on this core philosophy directly from our text. Normalization and denormalization are not inherently good or bad. They simply represent trade-offs in terms of performance of reads and writes and implementation effort. That last part, implementation effort, is absolutely critical. Choosing between a star schema, a complex Snowflake schema, or a brutally simple one big table isn't just about CPU cycles, it's about your engineering resources. Can your team maintain the complex data pipelines required to perfectly update a Snowflake schema, or is it more cost-effective to dump everything into one big table and let the columnar database engine brute force the analytics? Data architecture is entirely about matching the structural model to your specific organizational workload and capabilities.
So I'm going to leave you with this final provocative thought. The next time you experience a system slowdown, or you're sitting there waiting 10 minutes for a business report to load, think critically about the invisible scaffolding beneath it all. Look at your own application's data models. Are they truly optimized for your primary read and write workloads? Or are you accidentally forcing a strictly normalized transactional database to do a data warehouse's job? Understanding the continuous evolving trade-offs between normalization, joins, and analytical schemas is the absolute key to building resilient, scalable systems that can handle the petabyte-scale demands of the future. Thank you so much for exploring this deep dive with me today, and keep asking great, demanding questions about your data architecture.